All right, let's go ahead and get started. So welcome to FSI314. My name is Steve Merman. I am a Senior Solutions Architect at AWS. I'm dedicated to the Capital One account. So today we've got two exceptional speakers that are going to come up and they're going to talk about how Capital One designs and how they operate, how they function in a resiliency-focused or resiliency-centric environment. So first we're going to start out with Sharmila Ravi. And she's a Senior Vice President for Capital One Software Engineering. She's going to kick it off by kind of talking about, first discussing how they got to the cloud, how they've moved into the cloud, the focus areas there, what they focus on when it comes to resiliency, what they're looking at going forward. Then we're going to bring up Kathleen DeVault, who is a Vice President and Chief Architect for Card Tech, and she's going to get into the nitty-gritty, where she starts to talk about real use cases where resiliency is being implemented inside of Capital One, and cases where they really found a very unique way to solve some common problems that just really haven't happened in the space. They found very unique ways to go through resiliency and really solve it in a way that just works well for the financial services industry. So to kick it off, I'm going to hand it off to Sharmila.
Thank you, Steve. Good afternoon. Thank you for joining us. I'm always excited to talk about Capital One journey. When we think at the Capital One, everything starts with the strategy for us. Strategy, strategic execution, where do we want to be, and how does it look like when we're on the other side of the canyon? What are our customer experiences is going to look like? How does our associate experiences is going to look like? When you think about resiliency, I'm sure you're thinking about the 2 a.m. calls. Some of us have to jump on. Something went wrong. That's always the case, right? Something always goes wrong. So I want to talk about a little bit, culturally, how do we look at this at Capital One? When we set our sights to say, let us think more like a tech company, less of a financial company, we achieved it by ensuring that we are building our software in-house. Later, we declared that we want to be in the cloud. We built it natively. We got rid of all of our data centers. We're in a public cloud. And later, we started using all of our data, which Capital One is built on data, using the Snowflake, and we said, hey, here are all the tools that we're in need of. These tools will help us reduce the costs and operate the data better. And that's when Slingshot is born. Moving forward, we're looking at, now we're in the cloud, so how do we ensure our resiliency exceeds the expectations of the customers? And the real judge of our resiliency posture is always the customer and their experiences. With that in mind, we want to talk about how we think about it from top down in the organization. Resiliency isn't few engineers that have SRE titles that sits in an organization and will tell everyone else what the resiliency should be like. For us, resiliency starts from the business teams, defining our products and services, talking about the SLAs that we want to meet, and the customer experiences we want to see. From there, our product teams going through each and every user stories and jobs to be done, and be able to say at what point degraded services are okay versus complete outages. What type of information can be used as a stale data, just so that we are responding to the customer in the timely manner. And then it comes into the architecture. And we debate heavily. Kathleen will talk about that later. And uniquely, within the organization, we have combined architecture and SRE teams together under Kathleen's leadership, because we believe if we didn't architect it from the beginning, all we're doing in those midnight calls is just bouncing from region to region. And that's awesome. We get the customers back. That works really well when you have a major outages. All customers are impacted. But when you have a degraded service and few customers are impacted, that's when your architecture and the decisions you made up front becomes the most important thing. So I'll share the architecture diagram that we have at high level for the card technologies. This is the credit card technologies high level. I'm sure it looks very similar to whatever type of technologies you're all using. One thing I want to note is that none of our systems in any organization would look as cleanly as they look on this architecture diagram. They go through multiple layers, multiple messages, APIs calling APIs, and nested situations, redundant databases, multiple sources of truth in data. All of that is what creates the challenge for the resiliency. If all our systems are as cleanly organized as this diagram, it wouldn't be that hard, right? And think about it. As you build the resiliency, you're not just looking at your web and mobile applications and saying, do I have a great resiliency there? You're also looking at your customer experience ones. When they call in, when they try to digitally service themselves, how are we supporting the customers? Along with all of this, as a financial institution, we have quite a bit of responsibility on decisioning all the applications that the customers apply, fraud alerts, very important in the moment, so real-time matters, along with ensuring that every single one of the transaction, every single one of your swipe is working. We handle more than 7 billion swipes in a day. And one of the reasons that you stay at the top of the wallet is because your swipe works 100% of the time. So you can imagine the resiliency posture that you need in that particular scenarios. So as we go through this, we will talk more from this lens of architecture, how to think ahead, how to shift left your resiliency posture, not just about what do you do when you have an outage kind of situation. So that's the culture that we embraced at the Capital One. So I'm sure you all get asked the questions. You're all in the cloud. You should be resilient. Or you should be able to build everything to 4 nines, 5 nines, whatever we can afford, right, for the mission critical systems. I'm not saying we shouldn't. We should be building some of the systems, like my transactions processing should be a 4.9 or a 5.9, depending on your volumes. But not every single thing being built to 4 nines and 5 nines doesn't guarantee you the resiliency. This is just an example that we wanted to share, that you could build 5 interdependent systems because it's all distributed systems. You can build every single one of them to the 3 nines, but you will not achieve 3 nines at the end because inevitably one or another system will be down or will give you the errors. So just a fun example to say that even if we waste all the investors' money on building systems, doesn't guarantee the resiliency at the end. So we want to talk about a little bit of end-to-end flows, because resiliency to me just doesn't mean, again, just being in the cloud and bouncing back and forth between the regions. Resiliency is about the way you think about it. A customer came in, applied for a credit card. You are calling multiple systems here, right? Customer is filling in an application. They're giving you address information, for example. And your address verification system is down. So what do? Do you let the customer move forward to the next step? Do you continue to retry? Or do you use a stale data? These are the decisions you're making up front to make sure customer has the proper experience. And again, it doesn't hurt to do the retries in this particular case because it's address verification system. It doesn't hurt to represent back to the customer saying, you have another account with us, is this the address you're talking about? But at the same time, if my credit bureau check system is down, I wouldn't want to retry that. That's going to affect the customer credit line. So these are the decisions that you'll be making upfront. We want to just showcase to you that when you think about the end-to-end flow in a distributed system, you should be thinking about everything going wrong all the time and what should the customer experience should be, and that should be designed in from day one. You all know the CAP theorem. This is one of my favorite ones, and we debate it the most at Capital One. Challenge, right? Don't we want to be in the center of all of that? Always have the consistency, always be available, always have the partition. So that's the dream. Again, coming back to the reality of resiliency, we make decisions all day long. If it is a core processing system that is processing multi-million customers and their swipes, I want it to be always available and partitioned and ready to go. But if I want to run analytics, on the data I have and say that this analytics should tell me if I should increase credit line for a customer. I can wait to be consistent. I don't need the consistency that well. At the same time, if customer is swiping a card and their limit is 4,000 and they're already at 3,000 and the new swipe is 2,000, I do want to know in that particular scenario. Consistency becomes important. So within the same system, within the same user stories, in one case, consistency is your top priority. In another case, you can wait to be eventually consistent. These are the discussions you want to have upfront so you're making the right decisions as you move forward. This is a fun one. We think of resiliency as engineers all day long. Our customers see our resiliency through the lens of reliability as well. Imagine, as a company, you're sending out a fraud alert. One time your fraud alert is wrong, or you didn't provide the right information, your data is inaccurate. Can you imagine the customer feeling like your systems are resilient? Again, resiliency is always judged by the customer and their experiences. We heard the guru, right? Everything fails all the time. And we have very good example of when a cloud environment have failed us in a control plane, how we recovered, and Kathleen will go into the details. And again, we designed for most failures, and that is what helps us as we go through it. And when we're in the outages, as you all know, we continue to hire the new tech talent and training them. They may not be the people that were part of the architecture discussions or even the development at that point. So the playbooks, ensuring you have the right playbook, that most of the time when you get up in the middle of the night and you know what you need to do to recover from the customer and prioritize customer recovery at all costs, that becomes the most important part. Again, we touched on some of this, but designing for failure becomes the most important thing. How do I isolate it? How do I ensure I build for redundancy? How do I have a backup databases that will stay as a passive or maybe active, depending on your consistency needs? Ensuring that you be able to retry, and at the same time ensuring that we don't hit a storm of retries, right? Retrying is another technique that we all use often, and we get surprised by it in the outage situations. Wait, I turned it back on, now I'm in a retry storm, and now I'm going down again. So spacing it out and ensuring that you're designed for that intermediate time becomes the most important part. And circuit breakers, we talked about this already, but fallbacks and recovery. What is okay? When is it okay to ensure that you presented a stale data? There are times, instead of showing page not found or a complete error, I would much rather show you 15 minutes ago, this is your balance. I do not have a current information. That is much better than saying, I don't have any information on you, your app won't even load. So you have to think about these scenarios as you're going into the design. Degraded modes, caching. This is one of the things that we use somewhat heavily at times in our architecture. Because, remember, although all Capital One systems are built cloud natively, and we have multi-zone, active, and every single scenario you can imagine on the cloud side, we still have some third-party vendors that sit in mainframe, right? And we're still depending on their data and ensuring that they can provide us what's needed. Our customers, on the other end, are expecting everything to be real-time and very accurate. So that's the juggle that we all do, and that's where caching mechanisms will come into play. Monitoring and observability, I don't have to tell you guys this. This is when we find out we don't have monitoring, right? When we're in an outage. We weren't just monitoring that. So doing enough plays early on and ensuring that you are going through whatever methodologies, chaos engineering, or we have something called tracks internal where we do the failovers, planned and unplanned. Those type of activities is what will catch some of the monitoring, but it's almost ironic, multi-years into the cloud, we still, when we talk about an outage incident at the RCA, it always, almost ends up being the monitoring missing. So keep in mind. So here is a example we use for a resilient design. In this particular scenario, our web and mobile applications are coming in, asking for an API to get a data. And we have an external system. And those of you that know, external mainframes, they need love, feed, and care every week, which means their RTO is about 6 hours occasionally when it's planned. Unplanned, I don't have to tell you. So in those scenarios, how do I ensure I have an active system sitting in my area so that I have cached information? So we use global tables here, DynamoDB, and we are pulling information actively from the mainframe, storing it, hoping that we never have to use it. But if we do, we have as current data as we possibly can be right before the systems are down. So this is a way you can architect for resiliency, even in a mixed mode. Here is another detailed view of our core systems. In this particular scenario, we are using similar mechanisms. Again, caching is involved. But we're also using a streaming mechanism that we're bringing in data from the mainframe into our core. And we're using both the REST APIs and the GraphQL queries. This is one of the efforts where we are trying to ensure that we are not failing because of unnecessary data. Most of you know when you built on older systems over time, you're used to taking the payloads, whatever is given to you. And later on, you realize I don't need these 169 attributes. All I needed was 3 out of this. But you keep getting 169, and if there's an error on getting all of those, then you end up with an API error that you're dealing with. So we're also looking at GraphQL in this particular scenario to say, how do we reduce that? How do we ensure, while providing backward compatibility with the REST APIs, how do we ensure that deliberate attempts are made to reduce the unnecessary data moving forward, back and forth, which you can imagine is also a security concern in general. So those are the general examples that I wanted to give you. Before I pass it on to Kathleen, as I shared, she runs our organization that has small but mighty, I'll tell you. They're some of the best architects and SRE engineers, and they give us a challenge. I run the developers teams. So when we actually get into the room, these are the leaders that are challenging us constantly on the right architecture and ensuring that there is a resiliency in place. They join all of our incidents to ensure that they're listening in, to ensure that the next design and next architecture cares for it. So please give a warm welcome to Kathleen DeValk.
Thank you, Sharmila. And what an amazing and interesting, but yet complex set of problems. And honestly, this is one of the things that keeps me coming to the office every single day, because every day there's something interesting and a new problem to solve. We start out with a very cloud-native, cloud-first approach to all of our architecture and design. And you can see from very simplistic standard patterns, we deploy most of our compute either as Lambda functions, containers running in ECS or Fargate. We provide a lot of capabilities around how our systems communicate with each other. They communicate this with queues and SQS, with streams, with, we use AppSync and GraphQL scenarios. We use some step functions to orchestrate things. And EventBridge gives us a mechanism for sending events back and forth. Underlying all of this is robust, purpose-built, commercially hardened databases. So we leverage Amazon RDS Aurora primarily, and often cases we use DynamoDB frequently when we're running in a multi-region scenario. We use global tables, and we use a lot of S3 storage for our data lakes, our analytical processing, and our machine learning. As you can see, everything is deployed in a multi-region scenario with multiple AZs. So standard configuration. This is the foundation baseline that we base everything else on. Let's take a look at a little bit of deep zoom on the actual multi-region failover scenario. So we deploy in the 2 different regions, and we deploy all of our services in multiple AZs. So we have automatic failover within the region, and our application load balancers would automatically fail over within a secondary AZ when we need to. We provide a control plane that monitors everything. And via the control plane can detect system failures. How does it do that? So first, applications define health checks. The health checks of the application are specific to the application. What does it mean for your application to be healthy? And what it means for each application to be healthy is unique to the application itself. So it's fine-tuned and designed by the application developers. Then we set thresholds, and we use CloudWatch alarms and CloudWatch alerts to set thresholds. Thresholds are determined in the design phase through load testing, performance testing, boundary testing, scalability testing to understand where we stress the boundaries of the system, and then we know where to set our thresholds. But we don't stop there, because as you run your systems and you monitor and you observe them, your SRE practice is in a continuous learning process. So you're continuously optimizing and fine-tuning your thresholds so you can get the perfect balance over time and improve over time. The important part about this is the control plane is monitoring through the health check. The health check can identify that an application in a particular AZ or a particular region has gone unhealthy. And the health of the local region is communicated to the control plane as well as to the secondary region. So each region knows its own health, and it knows the health of the applications running in partner regions. That way, we can make the right decisions about how to route traffic to the right region to get the best customer experience for our customers. So we use Route 53 for routing, and when the alert triggers and a threshold is hit, or if a health check fails and puts the application in an unhealthy state, it uses automation to reroute you through Route 53. In addition, that same threshold detector can also trigger automation that invokes your health self-healing systems. So if a particular node is down, we can recycle it. If there's damage to my connection pool, I can heal it. If a job has failed, I can restart it. Whatever's necessary. So you can use these thresholds and triggers to both update the health of the systems so that you can properly route, as well as to invoke your self-healing automation. What this does for us, it gives us a faster mean time to detect if we fine-tune those thresholds continuously over time. So we can detect things faster, and if we can detect something faster, we can respond faster and restore service to our customers faster. The second aspect is because it's fully automated and because you can leverage your thresholds, once you get them finely tuned, leverage your thresholds to trigger your automation. Your automation may invoke functionality to self-heal your system, recycle an instance, reconnect to the database, recycle a database connection pool, whatever it needs to do, but you can trigger that through automation. And by doing that, you don't have to wait around for somebody to manually trigger something. The system will automatically self-heal itself. So the combination of putting these systems in place, optimizing and fine-tuning them over time, and invoking automated processes to fix your systems when they're broken is the key to that. And that fine-tuning that trade-off between cost, performance, and availability is the sweet spot, because you don't want to set your thresholds too low. That could increase your costs, but if you stress your system too much, you might not respond fast enough and trigger your scaling properly. Second example, so that is just a standard multi-region failover scenario. But what about these really important resilience scenarios that Sharmila had mentioned? When you process a credit card transaction, you want it to always work on the first try and as quickly as possible. So what we want to do is, in many scenarios, we'll apply more of an active-active pattern versus the first scenario, more of an active-passive pattern. In this scenario, we're also using Lambda and ECS or Fargate to run our containers or our functions. And these special cases, they may involve some complex infrastructure, so we have other special cases, but primarily running on those compute technologies. The data plane We leverage the data plane, as I mentioned, both S3 for our data lake storage, our analytical storage, our offline storage, but we also leverage DynamoDB global tables in most of our multi-region active-active scenarios. The key point there when we're balancing the CAP theorem is understanding that's about 1 second latency in replication between regions on DynamoDB global tables. It's less than 1 second. But 1 second, when you're processing a transaction that has multiple hops and involving multiple systems, that 1 second can be a lot of time. So understanding how long it takes for data to replicate influences how you design the system. The other interesting pattern is over-provisioning. You'll notice here, right, we've over-provisioned at about 120%. Why do we do that? We over-provision, and it's gonna be more expensive. So this is a balance of trade-offs. But by over-provisioning, we are able, at any point, if any single system goes down, if a node goes down, if an EC2 instance goes down, if an AZ is offline, we can redistribute the workload and absorb the capacity without degrading services to customers. The important part is knowing that that active-active scenario with over-provisioning is gonna increase your cloud spend. It's gonna increase your cost. So knowing when to utilize this scenario versus an active-passive scenario is gonna be key to your business. It's all business-driven, use case-driven, and it's, again, balancing of availability and reliability versus cost optimization. So taking this on a little bit further and doing another double click here, what we have is we have sometimes when you're processing a transaction, it involves multiple hops. So think of your standard credit card transaction. You swipe your card, we get the transaction, we detect if there's fraud. If there's no fraud, we try and process the transaction. We determine whether or not you have enough balance available in your account. And if you don't have enough of balance, sometimes we might decide to extend additional credit on the fly. So a lot of things are happening, and it has to happen in seconds, in hundreds of milliseconds, from system to system communication time. You're looking for really fast performance, and you want to make sure that there's consistency through the transaction end to end. Sharmila talked about the different use cases, some being more tolerant to eventual consistency. This is one of the scenarios where having consistency through the beginning to the end of your transaction can actually make a big difference in the outcome. And since you need to execute it as quickly as possible, you might want to keep the processing close together. So in one scenario of one of our game days where we were practicing east-west failover, we detected a scenario where the API gateway is failing over from east to west, and we were testing that scenario. And we had a long invocation chain that was undergoing performance testing at the same time. What we observed was the first step of the process executed the function and then called over to west. And then West said, oh, that service is running in the east, and it called back to the east. And that cost 200 milliseconds. So imagine you have a 10-step, 10-hop invocation chain. That can add up to quite a lot of latency. So being able to process the transaction locally makes a lot of difference in that end-to-end distributed transaction. So we use a combination of two different techniques to route the workload. The first is when you access the application through a user interface, we use more of a latency-based routing. And the latency-based routing should attach you to the fastest, most performant endpoint that you can access. Once you're inside the ecosystem and the UI is invoking a chain of APIs, we try and use more of a geo-based routing once you're inside. And by doing that, it tries to keep the processing of the invocation chain close together, so you don't wind up accidentally hopping back and forth between two regions and incurring that extra latency along the way. And this saves a lot of processing time. I mean, depending on how complex your invocation chains, it can get quite extensive. So by invoking this latency-based routing, we can keep the transaction close together. We can have better consistency through the end-to-end transaction because we're not incurring any replication time between regions, and we can execute the transaction much, much faster because we're not adding additional hops and additional latency communicating between the regions. So let's look at an architecture that is currently helping us achieve this. This is kind of the next wave of microservices architecture at Capital One. So everything is a microservice, and we use good isolation, and we have good boundaries between domains. But as we realized in looking at the architecture from a customer point of view, so we have a philosophy of a customer-back architecture. The customer-back architecture takes that really nice high-level architecture design that we showed up front, and it puts it in the lens of the end user, of the customer, because it's not as simple as all that. When a user executes a function, it traverses many of those different systems. And by providing this cell-based architecture, what we try and do is within a single cell, we try and execute the end-to-end invocation chain. So we deploy our services, we still have microservices, we still have the ability to deploy and scale them independently of each other. We still deploy them in that same general pattern that we showed earlier. So my containers are running on ECS or Fargate, they're running in multiple regions. But when I execute an invocation chain, I try and execute that invocation chain end-to-end within a single cell. And what I do is I then only fail over to an alternate cell when I have to. By doing this, I allow myself to try and process an end-to-end transaction as close together as possible, which improves my performance and it increases my consistency. So I achieved two really great outcomes for my customers by moving into this architecture. And with proper health checks in this system, we use a concept of developing a concept around fitness function. Fitness function will test the entire end-to-end use case from a customer perspective to make sure it executes end-to-end. And that is key and critical to not defining the health of a component, but now we're defining the health of an end-to-end user process that represents something our customer wants to do. And we can tag a particular cell as healthy or unhealthy in the same way that we're tagging components or microservices in healthy and unhealthy status. So this is an emerging pattern that we look at now to improve these resiliency postures. But what about the control plane? So this is what everyone forgets, right? It's easy. We all think, oh, I need a microservice, and I need it to run in multiple AZs, and I need it to be multi-region, and I need to have my failover scenario, and that's great. But what about the control plane? Many people forget about this. If your control plane is not highly available, when something goes wrong, that's going to be a problem. If your observability is not highly available, and you're running your observability platform in the same region that goes down, you might be blind, you might not know what's going on, you might not be able to deploy a change, you might not be able to actually correct the problem. So it's really important not just to think about the resiliency and the reliability of the software applications, but we really have to think about the reliability and resiliency of the tools and the systems that help us manage and run our production systems. And as Sharmila mentioned, the beautiful part of architecture and our SRE practice coming together gives us the perfect opportunity to design systems well, to instrument them well, to run them well, and to observe, learn, and continuously improve. So don't forget about the control plane. It is as important, and maybe in some cases more important, to make sure that it is highly available. And how did we learn that? My very first incident at Capital One was December of 2021. Anybody remember this? Route 53 went down. And there were errors, and we didn't know what was going wrong. And a lot of challenges faced us as we tried to work through. And it was a wonderful learning experience for me, and why I'm so passionate about that topic now at Capital One, my first incident. So what did we learn? Well, first of all, Route 53 went down, which resulted in a lot of system errors. We were seeing the system errors. AWS was seeing the system errors. We got on the phone. We worked together to work the problem together and shared what we were learning and what we were seeing together. And as the scenario unfolded and as we went through a root cause analysis, there were a lot of really valuable lessons learned. So the first was monitoring. If you can't see what's going on, you're blind. If you don't know what's happening, you can't do anything about it. So what we found was some of our monitoring systems were not multi-region. Some of our monitoring systems were impacted by Route 53 being down because we couldn't route the data from our applications into the monitoring systems. So we lost a little bit of visibility. The second one was internal deployment systems. So our CI/CD pipelines were running in US East, and they were calling APIs running in US East. And the AWS APIs in US East weren't that reliable at the time because Route 53 was experiencing this issue. And so we had a difficult time in recovering and forcing those failover scenarios because we could not invoke some of those CI/CD pipelines that were running in the East. Second was we couldn't get access to the console. The console was down. So the backup plan, log into the console, that wasn't working. So we were very reliant on these APIs and these systems, and that made troubleshooting the failure much, much harder, and the monitoring was unreliable, made the failure much harder to troubleshoot in the moment. And it was Christmas time, which doesn't help. So the next thing we learned was about continuous improvement and why continuous improvement is so important and why it's so important for us to learn from these incidents. This incident created unexpected behavior from the clients of the system. In AWS report, it was unexpected because when the system went down and Route 53 was failing, well, what does everybody do? Everybody retries, right? And that created a retry storm. And the retry storm exacerbated the problem, caused more slowdowns, more bottlenecks. And so then it became even more difficult. So what did AWS do? They responded very quickly and tried to alleviate the bottleneck. First step, alleviate the bottleneck. Why? Even if you can't get your system completely back up and running, get some functionality going. Alleviate the bottleneck, get some functionality going. It is better to have some uptime than no uptime. So that was the first step. And that gave the team a little bit more time to continue troubleshooting the problem and addressing the problem. The second thing, the other thing that we learned was understanding your system at all levels. So we already talked about, I have an application, I want to achieve 3 nines, and I have 5 other dependencies. What does that mean to my application's availability? And I have to mitigate those risks. So understanding where your dependencies are and understanding how that impacts what you're doing is key, and that's really critical. So because Route 53 APIs were down, we had difficulties updating DNS entries that would help reroute things to a secondary region. And the manual workarounds that we were using, we could manually update, but then there's propagation delay, about 15 to 20 minutes of propagation delay through the DNS cache. So we would make a change, but we couldn't see the effects of that change right away. And because our monitoring systems were also impacted, we were not seeing the monitoring results. So that made it very, very difficult. So understanding how the things you're dependent on actually work underneath the covers informs you how you can design workarounds or fallback scenarios when you encounter incidents or issues in those foundational systems. The other aspect was in the control plane itself. So the control plane, not just our control plane, but the AWS control plane was impacted. Route 53 is down. What do you need to do when you add a new EC2 instance to your cluster? You need to set the networking configurations. So because of this, systems that were running were okay. But if you had to trigger an auto-scaling event, you couldn't. So that was impacted. Or if you had a system that was not behaving properly or got in that unhealthy state we talked about earlier, and you want to recycle it, you couldn't. So understanding not just your layer, but the cloud infrastructure layer, and being able to mitigate those and being able to have backup plans. When you really know how things work under the covers, it's much easier for you to design and resolve some of these issues. So make sure you have visibility, have a redundant control plane, understand your dependencies, understand how things work, get things back up and running, even a little, if it's not 100%, even a little functionality is better than none. And every chance you can get, learn, because it's not the expected that catches you in production. It's the unexpected. It's not the happy path that gets you. It's the stuff you were not expecting. So we start with traceability. If you can't see what's going on, you cannot do anything to troubleshoot it or resolve it. So traceability instrumentation is key. And you can't just log data from an application or a microservice when you have a highly complex distributed system like we showed earlier. You need to know what happens end to end. It's not just what happens within a single application or service. It's what happens when a user tries to do something end to end. So we start by providing a robust logging system. We inject correlation IDs when user functionality is invoked. And we try and propagate that correlation ID through the end-to-end processing chain. And this is something that's a work in progress. Some systems are better than others, but we're continuously improving this because the key is if you have ability to correlate all of the hops through your entire stack and you know what went on in that end-to-end invocation chain, you can start observing where failures occurred, you can do better failure analysis, you can plan for better retry scenarios and fallback scenarios in the future, but the key is having that instrumentation and having that visibility and tracking that end to end. We also employ real user monitoring, so everything that gets accessed by a user gets logged. Using real user monitoring, we can see what's happening right now on the system as users interact with the system. There's also synthetic monitoring, but in our world, synthetic monitoring is a little bit more challenging because at the end of the day, you don't want to create transactions and impact actual money. So that is also a scenario you can use, but this real user monitoring really tells you what's happening to the systems right now in real time as users interact with it. By doing this and by tracking invocations of APIs, HTTP response codes, response times, we can now see things that are occurring. And what we can do is we can start looking for early warning signals that are occurring in our logs that happened before the incident. And by analyzing what happened, how the incident happened, what happened leading up to the incident, and looking at these signals, we can start to envision a world where we can detect an incident before it affects a customer and start predicting and preventing incidents. And that is the world we're striving towards right now. So here's a couple of examples where you can observe the signals in your system and use those signals as early warnings to predict and prevent an incident. So say you have a long chain data processing pipeline, multiple steps. Track the latency end to end. What's the propagation delay between the first signal you get and when the end-to-end data processing chain completes? If you are tracking that end-to-end latency over time and you see an increase in latency over time, kind of trending, you can predict there's probably a bottleneck in the making. And if you set your thresholds appropriately, you can say, oh, there's a bottleneck in the making. Before the bottleneck starts impacting my customers, impacting the performance, before I start losing data, let me scale out my system proactively to address the bottleneck in the system. And so if you're monitoring this, you can predict and prevent. That's one scenario. Another scenario happened recently where we had some infrastructure management going on in the background, and we detected that one of the applications had increased its connection pool size, and suddenly its connection pool size was just huge, and it was continuing to grow. And so by looking at this, we understood that something unusual was happening in the infrastructure, and we were able to go and respond to it and address the issue and alleviate that problem. So look at your connection pool. If something's growing out of control, whether it's connection pools, CPU, memory, if something's growing out of control and it's on an upward trend and you can't explain it, something might be going wrong. And you can use these signals to early detect, reduce your mean time to detect, and then react quickly and reduce your mean time to resolution. Increasing response time is the easy one. I mean, if your application has a consistent response time that you expect on average for customers, and you see that increasing over time, something might be wrong. There could be a performance problem, there could be a bottleneck, there could be, anything could be wrong, but the response time is also another really great early warning indicator. The last one that we are implementing now is anomaly detection. So if you're expecting a certain number of transactions per second or a certain number of requests per hour, and there's an anomalous reading, there might be something wrong. So if you have a huge number of login failures, you might want to probably look at that. If you have a lot of retries occurring, something might be going wrong, and that might be an indicator that there's other things going on, and maybe you want to intercede before the customer gets impacted. So the whole purpose of these is to really look at what happens leading up into an incident, and how can I improve my monitoring and observability, improve my instrumentation to track these signals so that I can predict and prevent failures before a customer is ever impacted. And that leads me to the continuous improvement. Because this is all great, and designing your systems is great, but when the rubber hits the road, when your system hits production, it's never going to behave the way you thought it was going to behave. So there's going to be things that go wrong. There's going to be things that impact you, things you didn't imagine, things you didn't know of ahead of time. And so by understanding this, then it's not about being perfect in the first place. It's about, as things go wrong, as you learn, as you observe things, you learn. And then you implement your learnings to improve. Again, that's why architecture plus SRE is a brilliant circle, because you feed what your SRE team learns back into your architecture and design. You build better architectures tomorrow because you learned what went wrong yesterday. And so that's the whole idea about continuous improvement. We do this at CARD through our SRE community of practice. We do not run a central SRE team. We have a small but mighty central SRE team, but we partner with the domain owners. So the domain architects and the domain developers, they know their domains better than our central team does. And they understand the complexities, they understand the business needs, they understand the non-functional requirements in their area. They also know nitty-gritty in the deep details how things actually work. So we partner and we build a community. And around this community, we strive around excellence by defining standards. We set up metrics that helps us monitor our success and measure our success. We look at the metrics together and hold ourselves accountable for meeting those metrics. We focus on reliability through observability improvements and through resilient architectures, as we discussed and shared some of the new journeys we're on now to even make those architectures more resilient. And then we focus on automation, Because if you can automate it, it's repeatable. It reduces the toil for our developers, and we have a repeatable, accurate process that's faster and easier and takes a lot of the toil and burden off of our development team, and that we implement it. And by working together as a community, we can implement something once and share it amongst all of our colleagues. And we drive these metrics up, driving down incidents, driving up uptime, increasing our deployment frequency, reducing the amount of manual tasks to optimize the efficiency of our development teams. We also create a culture of operational excellence. That's key. It's not just setting metrics and letting them be. It's creating a culture around operational and engineering excellence that makes us want to be better tomorrow than we were yesterday. As I mentioned, this set of complex and interesting problems, this is what gets me up in the morning. It's what brings me to the office because it's interesting. And this culture of operational and engineering excellence brings us together as a group, striving for the same goal. I want to be best in class. I want to be the best. And that touches on our little human characteristic of competitiveness and brings out that nature in us so that we strive to continue to be better. And we implement these through a couple of different pillars. We have our testing pillar, which is about test automation. It's not just functional testing, it's also non-functional testing, performance testing, security testing. It's also about observing your infrastructure and making sure your infrastructure reflects the governance and requirements non-functionally that it needs. So it's all of those aspects. The next pillar is about observability because, again, you need to observe the system, you need to capture your metrics, you need to hold yourselves accountable to your metrics, and you need to be able to see what's going on. And so, as Sharmila mentioned, every time we look at an incident, we find an opportunity to improve our instrumentation and our observability so that tomorrow we have more information and we can detect that. And we create this operational excellence checklist, so as we learn from incidents, we add things to the list. Hey, if we had done this the last time, we probably wouldn't have had this incident. So we continuously improve this process by learning from what happened yesterday. We focus on resilient architectures. We do failure mode analysis, especially in these long invocation chains, to understand where failures could occur so that we can plan the fallbacks and the failover scenarios. And the focus is on operations. Again, operational excellence. Making sure we have solid deployment strategies, solid rollback strategies, make sure we have run books, because you don't want to figure it out at 2 o'clock in the morning. You want a nice little playbook or run book that says, here's what you do. So at 2 o'clock in the morning, maybe your brain's not as good as it is at 10 o'clock in the morning. So having these things in place helps us scale the process and repeat the process. And automate as much as we can. If we could automate everything, that would be the ideal goal. The more you can automate, the more it's reliable, it's repeatable, and you just hit a button, and it doesn't matter it's 2 o'clock in the morning, because the automation takes care of it. We center our practice around these 3 core pillar principles on highly reliable systems, is really understanding the operating point and optimizing your system within the operating point you're targeting. And so that's around your SLAs, your SLIs, your SLOs. What is my optimal point? And how do I make sure that I'm balancing that need? Those come from your business case, the non-functional requirements from your business case. The second is architecting our systems and instrumenting our systems to reduce the mean time to detect and reduce the mean time to resolution. Because if I can find it faster and I can fix it faster, less people are going to be impacted. So always my goal is no customer has a problem, ever. That's my goal. So the faster I can detect it and the faster I can resolve it, the better outcome it is for my customers. And the last is understanding your blast radius, defining appropriate blast radius to address when an incident does occur, because they will. No matter what you do, something is going to go happen at some point So reducing your blast radius is key critical to that, because if one system is down, maybe the rest of your ecosystem is still up and running and you have some functionality, right? Better some uptime than no uptime. And the second is really around those human operations, and that's where knowing how your systems work, getting on the phone, looking at the incident together, sharing your experiences, and that's why we scrambled together through our SRE team, as Sharmila mentioned, together with the developers in CARD to come together to look at issues and solve them together, and making sure that we are continuing not just to improve our systems, but improving our humans, our people, improving their knowledge as well as their ability to respond and analyze. I mentioned that optimal performance boundary. So when you're really looking at your system, you could have everything ultra consistent, you could have everything active, and that's gonna get very expensive. So what do you really need? And how do you find the sweet spot, right? Because you wanna make sure that you're operating within your boundaries, not too close to any of your edges, but at the optimal sweet spot. So you're providing all the non-functional requirements to your customers with the right cost point, with the right overhead. The second is, again, about this same concept, mean time to detect, mean time to resolution. It's hard to predict when a component will fail, but when it does, the whole goal is to recover automatically and gracefully. So this is our constant goal, and that's why we strive more and more every day towards getting to this point where we can see leading indicators of incidents, we can detect them, we can predict them before they happen, and we can respond and address them before it actually impacts our customers. And it's that, again, delicate balance between cost, performance, availability that you're constantly juggling. Limiting the blast radius is also key. So we have microservices, we have this new cell-based architecture. This allows us to limit blast radius. We also use regional isolation, zone isolation, and things like this that help us. So one system is down, we have caching mechanisms maybe that protect the dependent systems from that outage. And also increasing your transparency and driving accountability. That's key, right? Because if it's just my problem, okay, I'm gonna work really hard on it, but if it's all of our issue, if together we hold ourselves accountable, our engineering team, our product team, our operations team, our security team, our architecture team, if all of them come together and we all hold ourselves and each other accountable by looking at the metrics together, it drives that sense of accountability and that desire, again, to be better and better tomorrow. But it is key. If you lack that, then it's a debate. Do we spend more time on features? Do we spend more time on security? Do we spend more time on reliability? If you set the metrics, and the metrics are important to your business, and you drive yourselves towards improving your metrics, and you're aligned on measuring what matters, and you're aligned on that, that helps drive this accountability. So, to wrap it up, practice makes perfect. It's all great in theory, but you gotta put it in practice. So we have game days. Game days help us test our failover postures. We have fire drills. Fire drills are great because it helps you practice in a safe environment what's gonna happen in the middle of the night. Is that you don't wanna be practicing the exit to the building while the building's on fire. You wanna know the way out ahead of time. So fire drills are a really good way for us to practice our incident response. And have a playbook. Don't just wing it. In the heat of the moment, you don't want to have to be thinking about what you need to do. Have a playbook and follow the playbook. If you're prepared, it's going to make the incident much easier. We implement chaos engineering. It's a new thing at Capital One. It's a growing movement. Chaos engineering tells us what we don't know. Not a happy path. It's not the happy path that goes wrong. Chaos engineering is going to tell us what we don't know. It's going to tell us how we behave. How does my system behave when the things I'm dependent on are not doing their job? That is what it tells us, and it's really fun, and it's really exciting, and hopefully your developers, because it's kind of like the hot topic, can get into it. It's all about continuous improvement. It's not about how you are today. It's about how you continue to get better and better for tomorrow. And then make sure you scale it. Centralized may not work. Maybe it does if you're a small team, but if you're a big team, involve your domain experts. Bring everybody together in a community. Share lessons, learn from each other. And how are we able to do this? Because from the top to the bottom, from the developer to the CEO, we think like a technology company, not like a standard bank. Thank you. Appreciate your time. Make sure you fill out the survey.